The universe did not begin in silence. Even now, as you breathe gently in the dark, the cosmos around you is still expanding, still cooling, still carrying the faint afterglow of its own creation. And yet, there's a deeper question, one so quiet, so rarely asked aloud, that it seems to hover just beyond thought. What was the universe doing before the Big Bang? Was there a before at all? Or does time itself dissolve when you try to peer past that first luminous moment? Before we drift into this forbidden frontier of cosmology, if this calm journey brings you even a moment of peace, I'm deeply grateful you're here. A gentle like or a soft tap on subscribe helps keep these quiet explorations alive. Now, we drift into part 1. Part 1. Why the question? Before the Big Bang is so difficult to ask. Before we can search for answers, we must understand the question itself. If time began with the Big Bang, as many cosmological models propose, then asking what came before may be like asking what lies north of the North Pole. Yet your mind naturally reaches for a preceding moment, a hidden chapter. In this part, we gently explore why the very structure of time becomes uncertain the closer we approach the beginning. When you imagine the universe, you might picture a vast space filled with galaxies and light stretching outward in every direction. You might picture stars being born, planets cooling, or even the slow swirl of cosmic structure. But beneath those images lies something more fundamental: time itself. Every event you have ever known, every breath, every sunrise, is a sequence. One moment follows another. It is difficult to imagine existence without that sequence, without the soft progression from before to after. Yet when we trace that sequence backward, all the way toward the Big Bang, the very idea of before begins to dissolve. To understand why, imagine you are following a river upstream. Each bend leads you to another, each merging tributary taking you closer to the source. But the source itself is not a river at all. It is a spring, a point where flow simply begins. Asking what came before that spring is like asking for a river that existed before water. At some point, the question stops having a meaning tied to the thing you are studying. In cosmology, time functions much like that river. It flows smoothly now, carrying every moment along with it. But the closer we move toward the origin, the less familiar the landscape becomes. Modern cosmology teaches that time is not an independent backdrop against which events unfold. It is intertwined with space, forming what physicists call space-time. According to Einstein's general relativity, space-time bends and stretches depending on matter and energy. This means time is not a universal rhythm ticking everywhere identically. Instead, it is malleable, shaped by motion and gravity. Near a black hole, for example, time slows dramatically. At the E2 surface of the Earth, time flows just slightly slower than it does for satellites orbiting above. Even the 1 centimeter difference between your head and your feet produces a measurable shift in time's flow. That small fact alone whispers a deeper truth. Time is not fixed. It is something that can change. But to understand why the question of before the Big Bang falters, we must look at what happens when we push Einstein's equations to their limit. As we approach the earliest fractions of a second after the Big Bang, far earlier than any star or galaxy, the universe becomes unimaginably dense. Temperatures climb beyond what any modern experiment can recreate. The smooth fabric of space-time, described by relativity, begins to twist under extreme conditions, while quantum uncertainty amplifies into chaotic fluctuations. In this environment, relativity can no longer provide a coherent description. It predicts a singularity, a point where density becomes infinite and where time, as understood by the equation, simply ceases to exist. But singularities are signs not of physical reality, but of a theory reaching its breaking point. They tell us that our mathematical tools are incomplete, not that the universe becomes meaningless. Still, the implications are profound. If time emerges from the structure of spacetime, and if spacetime breaks down near the Big Bang, then the concept of before may have no physical footing. Imagine holding an old photograph. You can trace its history, when it was taken, who developed it, where it was stored. But the paper itself had a moment before it contained an image, a blankness not yet shaped into meaning. Now, imagine time in that same fragile state, not yet imprinted with moments. The beginning of the universe may be that blankness, a point where time had not yet assumed its familiar form. This idea becomes even more intricate when we introduce quantum mechanics. Quantum physics does not describe time as a smooth, continuous flow. At extremely small scales, far smaller than atoms, time appears grainy, fragmented into intervals where the familiar rules of cause and effect blur together. In these fleeting intervals, the distinction between before and after loses clarity. Events do not unfold in sequence, they exist in probabilities. This means that when we trace the universe back to its earliest instant, we encounter a regime where space and time are no longer classical ingredients. The laws that govern everyday motion, gravity, acceleration, cause, and effect, begin to unravel. Cosmologists call this the Planck era, the first 10⁻43 seconds of the universe's history. It is a time so early that every equation we know fails. Without a theory that unites quantum mechanics and gravity, we cannot say what time was doing during this era. And without that, the idea of before is suspended in uncertainty. Still, the mind resists this. You may feel a quiet instinct telling you that something must have come before. The Big Bang seems like an event, and every event you have ever known has had a cause. It is a natural impulse. But the universe does not always follow the patterns familiar to human intuition. On cosmic scales, beginnings may not behave like beginnings, causes may not behave like causes. One way physicists frame this is by comparing time to temperature. Temperature measures motion of particles, but ask what temperature is at absolute zero and the question shifts. Below absolute zero, the concept no longer applies. In the same way, time may not exist in forms lower or earlier than the Big Bang. It may not be that something caused time. Rather, time may be a product of the universe's expansion itself. Another way to view this is through geometry. The North Pole analogy remains one of the most powerful tools here. On a globe, the northmost point does not require another point above it. North simply loses its meaning. In some cosmological models, time behaves the same way. As we approach the beginning, time becomes like the final point at the top of the Earth. There is no earlier, because earlier is not defined. And yet, we are not left with emptiness. Instead, we find a frontier, one where new theories may offer insight. Loop quantum gravity suggests that time may have a discrete structure. String theory suggests that hidden dimensions might give rise to time's behavior. Other models propose that time could have existed in another form, one unfamiliar to us, before crystallizing into the version we experience. All of this leaves us in a delicate place. The question of what came before the Big Bang reveals not a failure of curiosity, but a remarkable feature of the universe. It shows that our deepest instincts, the ones shaped by motion and memory, may not extend into the earliest chapter of reality. Time might not have started in a moment, but emerged gradually as the universe cooled and expanded. So as we close this first chapter, we hold the question gently. Not because it has no answer, but because the answer may require physics we have not yet discovered. And as we drift toward the next part of our journey, one truth becomes clear. To understand what the universe was before the Big Bang, we must first understand what time really is. Part 2. When time itself may have emerged from physics. If you could travel back through cosmic history, all the way to the first trillionth of a second, you would find that the flow of time behaves differently, slowing, bending, and finally dissolving into the physics of quantum gravity. Here, we explore the possibility that time is not fundamental, but born from deeper rules that crystallized only as the universe cooled. The deeper you journey into the early universe, the less familiar the landscape becomes. At first, it looks like a place filled with light, intense, blinding, and impossibly hot. Matter and energy weave together in a dense, radiant sea. But beyond that brightness, beyond even the moment light first broke free, lies a region where our best laws stop agreeing. The smooth flow of time that guides your life begins to tremble. Seconds lose their shape. And then, just a little further back, time itself begins to thin out like mist. To understand why, we need to explore what physicists mean when they say time emerges. In everyday life, time feels like a clock, steady, constant, 1 second following another. But the universe does not actually carry a built-in clock. Instead, time is woven into the geometry of space itself. Einstein showed us that space-time is a single fabric, curved by matter and energy. As the universe expands, that fabric stretches. As gravity intensifies, it bends, and in each of these distortions, the rate at which time flows quietly shifts. When the universe was young, its density was so overwhelming that space-time curved in ways we can barely imagine. In those early moments, gravity was not a gentle force. It was a dominant sculptor, shaping the rhythm of every particle. Under these conditions, even the smallest change in density could warp the flow of time. Seconds would not simply pass, they would deform. But go back further, into the era before 1/1,000,000th of a second, and Einstein's smooth space-time stops describing reality. Quantum effects, normally subtle ripples, become violent waves. The universe becomes granular at the tiniest scales, flickering with microscopic fluctuations. In this quantum ocean, space-time ceases to resemble a fabric. It becomes a foam, a surface shifting so rapidly that time can no longer be defined in any ordinary sense. Events lose sequence. Cause, as we understand it, loses its anchor. This era, known as the Planck epoch, is where physicists believe time as we know it may not have existed at all. Just as water must cool below a certain temperature before ice crystals appear, time may have required the universe to expand and cool before it could solidify into the smooth dimension we experience today. But why would time behave this way? One clue comes from the nature of quantum mechanics. In the quantum world, particles do not have fixed positions or paths. They exist in probability clouds, shifting from one possibility to another. Without well-defined trajectories, the idea of time, measuring how something changes, begins to falter. If nothing has a clear state, then there is no clear before or after. Time requires change, but change requires stability. In the earliest universe, stability had not yet taken shape. Another clue comes from the concept of entropy. The arrow of time, the reason you remember the past but not the future, is tied to entropy increasing. As the universe evolves, disorder gradually spreads. But at the beginning, the universe was in an extraordinarily low entropy state, smooth, uniform, and highly ordered. With no gradient for entropy to increase along, the arrow of time may not have existed yet. Time had no preferred direction. It may not have flowed. It may simply have been undefined. In this sense, time might not be fundamental. It might be a property that emerges only when conditions allow it, just as pressure emerges only when enough particles are present, or temperature emerges only when their motions stabilize into averages. Before that stabilization, concepts like temperature or pressure lose meaning. Time may fall into the same category, a macroscopic property born from many microscopic interactions. This idea is explored in several approaches to quantum gravity. Loop quantum gravity, for example, suggests that space and time come in tiny, discrete units. These units are not infinitely divisible. They are quantized, grains of geometry. When the universe was smaller than these grains, the structure of time itself could not exist. Only when the universe expanded beyond this scale could the grains connect, forming a coherent sequence of moments. String theory offers another view. In that framework, the universe's earliest state may not have been a point at all, but a higher dimensional landscape vibrating with energy. Time, according to some string models, emerges from the configuration of these extra dimensions, like a shadow cast by a deeper geometry. In this picture, the Big Bang was not the beginning of time, but the transition from one geometric phase to another. Time may have switched on when the universe crossed that threshold. These theories differ in detail, but they share one quiet idea. Time is not primary. Time is a rhythm the universe learned as it cooled. If this feels abstract, imagine a whirlpool forming in a lake. Before the whirlpool appears, water molecules move in all directions. There is motion, but no pattern. After the whirlpool forms, motion becomes organized. A structure emerges. Time might be like that, an emergent pattern of underlying physical rules. As scientists push deeper into these ideas, they use not only mathematics, but also the faint light of ancient radiation. The cosmic microwave background, the oldest light we can observe, carries subtle variations that hint at the early universe's behavior. These tiny ripples are a record of when time first gained direction. They show us when randomness began to settle into structure. Although they cannot see into the Planck epoch itself, they tell us that something profound occurred just after it. A transition from chaos to order, from undefined to defined, from timeless to time. Still, there is a mystery we must hold with care. If time emerged, what does that say about the moment before? Can we speak of a moment at all, or does the question dissolve not because it is unanswerable, but because the concept it depends on does not yet exist? This brings us to a gentle but profound perspective. The universe may not have started with a bang, but with a transformation. The Big Bang might not be an explosion in time, but the creation of time. It might be the surface of a cosmic horizon beyond which our language, our intuition, and our mathematics cannot yet reach. As we drift out of this chapter, one thought lingers like a quiet pulse. If time can emerge, then so can everything shaped by time: motion, memory, cause, and consequence. To understand the universe before the Big Bang, we must understand the universe before time. And that journey continues in the next part, where we follow the strange possibility that the universe may have arisen not from something, but from nothing at all. Part 3. The Quantum Fluctuation Hypothesis. A universe born from nothing. One of the quietest ideas in cosmology is that the universe may have emerged from a quantum fluctuation, an event in which empty space briefly allows energy to appear, then expands before it can disappear again. In this view, the universe does not come from a place or a moment, but from a law, an allowed tremor in the fabric of the void. To understand this idea, we must first understand what physicists mean by nothing. In everyday language, nothing suggests emptiness, a silent room, a blank page, a dark void. But in quantum physics, nothingness is not a desert. It is a restless sea. Even in a perfect vacuum, fields shimmer with energy. Particles flicker into existence, then fade, leaving behind only a trace of their brief appearance. This phenomenon is built into the mathematics of the universe. It is not optional. Even absolute silence hums with activity. When physicists say the universe might have come from nothing, they do not mean a complete absence of all physical structure. They mean that the universe could have arisen from the vacuum state, a background of potential governed by quantum rules that allow fluctuations to arise spontaneously. These fluctuations normally appear and vanish so quickly that they leave no lasting mark. But if one fluctuation were pushed into a special state, if it expanded rapidly enough, it could escape this brief fate. Instead of collapsing back into silence, it could grow into a universe. Ours may be such a universe. To appreciate how such a thing could happen, imagine a calm lake at dawn. Its surface looks perfectly still, but beneath it, water molecules are in constant motion. Occasionally, a small ripple forms, so small and short-lived that it barely disturbs the reflection of the sky. That ripple is like a quantum fluctuation. But now imagine that the lake is not water, but a field. And imagine that one ripple encounters just the right conditions to grow instead of fade. It spreads outward, growing larger, smoother, and more stable. In this analogy, that expanding ripple is the universe itself. But what could make a tiny fluctuation expand instead of vanish? This is where cosmic inflation enters the story. Inflation theory proposes that the universe, in its earliest fraction of a second, expanded exponentially, doubling in size again, and again, faster than the speed of light. This rapid expansion was driven by a field with enormous stored energy, a field that acts like a kind of anti-gravity. When a quantum fluctuation enters such a field, the field forces it to grow outward, transforming an ephemeral tremor into a vast, stable cosmos. The beauty of this idea is that it ties two mysteries together: the origin of the universe and the origin of inflation. If both can emerge from the vacuum, then the universe does not require a preceding structure. It arises from the rules that govern the vacuum itself. But this leads to a deeper question. If the universe came from a quantum fluctuation, where did the laws come from? Here, cosmology reaches a philosophical edge. Some physicists argue that the laws of quantum mechanics may be the most fundamental aspect of reality, not created, but simply existing. Others argue that the laws themselves may have evolved. But most importantly, the quantum fluctuation hypothesis does not require a pre-existing environment. It only requires that the vacuum obey the rules we observe today. And remarkably, many experiments confirm that the vacuum does behave this way. In laboratories, quantum fluctuations are not hypothetical. They can be measured. In the Casimir effect, for instance, two metal plates placed extremely close together are pushed inward by the pressure of virtual particles fluctuating outside them. These particles are not permanent residents of space. They appear because the vacuum cannot remain perfectly still. Nature, even in its quietest form, is dynamic. This restless nature of the vacuum suggests that the universe may not require an initial cause. It may require only an opportunity, a chance for a fluctuation to stretch into stability. To visualize this, imagine the universe in its earliest birth throes. The fluctuation appears, filling with energy. Inflation ignites, stretching the fluctuation to unimaginable size. The energy stored in the inflationary field converts into matter and radiation. Space fills with particles, quarks combining into protons, electrons spiraling into orbit. The universe cools, and structure begins to form. Stars ignite, galaxies swirl, planets gather dust, and billions of years later, a small creature on a small world begins to wonder how it all began. But the quantum fluctuation hypothesis carries a subtle implication, one that quietly reshapes your perspective. If universes can emerge from fluctuations, then our universe may not be unique. Quantum fluctuations happen everywhere, constantly, and each fluctuation has the potential to seed a new universe if the conditions are right. In this view, reality may be a vast multiverse, with countless universes budding from the fabric of the vacuum, like dew forming on a leaf. Each universe expands, evolves, and cools, some barren, some fertile, some large enough to host galaxies, and some too brief to form structure at all. If this is true, then the question, why is there something rather than nothing, becomes softer, less final. The vacuum itself may be the answer. Nothingness, in a quantum sense, naturally gives rise to something. Creation is not an event, it is a property of the void. Still, the idea of a universe from nothing raises a delicate conceptual shift. If the universe emerged from a fluctuation, the fluctuation itself does not exist in time. It is not preceded by an earlier moment. Instead, it is the beginning of time. This is one of the hardest ideas to hold. It means that the phrase "before the universe" may have no physical meaning, because the universe is what gives the word "before" its structure. In the quantum fluctuation view, the universe did not appear at a moment. The universe is the moment. At first, this may seem to remove mystery, but in a quieter way, it deepens it. Because now, instead of asking what triggered the universe, you are invited to ask what the vacuum truly is. What lies at the foundation of the laws that allow such fluctuations? What shapes the fields from which universes emerge? Physicists do not yet know, but every observation, from particle accelerators to the cosmic microwave background, points to a universe whose beginning does not require an outside agent, only the restless potential of quantum fields. As we come to the end of this chapter, you might feel the ground beneath your understanding shift slightly. The idea that the universe arose from a fluctuation does not diminish its wonder. It expands it. It shows that even nothingness carries possibility. Even silence whispers. And as we drift gently into the next part, one question glows softly in the dark. If the vacuum can create universes, what does the vacuum itself come from? That quiet mystery leads us deeper into the nature of emptiness, into a region where nothing is not empty at all. Part 4. What nothingness actually means in physics. Nothingness is not silence, it is not darkness. In physics, nothingness is a restless ocean of fields, endlessly jittering even at absolute zero. When scientists speak of the universe emerging from nothing, they mean this sea of potential waiting quietly beneath existence. In this chapter, we explore what that vacuum truly is and why it might not be empty at all. When most people imagine nothing, they picture a void, a featureless darkness without particles, without atoms, without light, a perfect emptiness. But the universe does not allow such a thing. Even the most pristine vacuum humans can create, even the emptiest reaches of intergalactic space are filled with activity. Invisible fields stretch through every corner of reality, humming quietly with energy. Particles appear and vanish. Virtual photons flicker in pairs. Quantum fields vibrate even when the temperature reaches absolute zero, a place where classical physics predicts perfect stillness. Yet, stillness is impossible. Something always moves. This is the heart of modern physics. Emptiness is an illusion. A vacuum is not a physical absence. It is a physical state, a configuration of fields at their lowest possible energy. But lowest possible does not mean zero. It means the minimum allowed by the laws of quantum mechanics. And those laws insist the universe can never sit perfectly still. If it did, it would violate the uncertainty principle, a foundational rule of the microscopic world. According to that rule, the more precisely you know one property, say, a particle's position, the less precisely you can know another, like its momentum. Push both to perfect precision and the mathematics breaks. Nature refuses to be nailed down, so the vacuum fluctuates. Even at absolute zero, tiny bursts of energy erupt. Particles materialize and disappear before they can interact with anything. This restless foundation is what physicists call the quantum vacuum. To appreciate how strange this is, imagine a dark theater before a performance. The stage is quiet, but the actors are just off stage, waiting breathlessly. The vacuum is that waiting. It is not yet a play, but all the ingredients of a play exist there, trembling with possibility. A tiny disturbance, an energy fluctuation, a ripple in a field, can set the entire story in motion. One of the most vivid demonstrations of this vacuum activity is the Casimir effect. Place two uncharged metal plates extremely close together, closer than a hair's breadth, and they will mysteriously attract each other, even though no force seems present. The attraction is caused by vacuum fluctuations, virtual particles pushing on the plates unevenly. They appear everywhere except in the tiny space between the plates where their wavelengths don't fit. The imbalance creates pressure. The plates move. Nothingness does something, and that is the key. Nothingness acts. It exerts forces. It shapes reality. This leads to a profound question. If the vacuum behaves like something, is it really nothing? Physicists answer with a quiet paradox. The vacuum is the ground state of the universe, its simplest, most stripped-down form. Yet this state has energy. That energy can curve spacetime, and that curvature can create expansion. In fact, the vacuum may be the reason the universe is expanding faster today than it did billions of years ago. This acceleration is attributed to dark energy, a mysterious force that permeates all of space. Some physicists believe dark energy is simply vacuum energy, the intrinsic pressure of nothing pushing space apart. If so, nothingness shapes the fate of the cosmos, but nothingness also shapes the origin of the cosmos. When cosmologists theorize that the universe emerged from nothing, they do not mean that existence sprang from a magical void. They mean it arose from the vacuum state, where quantum rules allow energy to appear briefly without violating conservation laws. Under usual circumstances, these energy blips disappear almost instantly. But if the conditions are right, if a blip occurs in a field capable of igniting cosmic inflation, that tiny moment of emergence can balloon into an entire universe. This raises a quiet but startling idea. Perhaps the universe is what happens when the vacuum is disturbed. To understand this more deeply, we need to explore the quantum fields that fill the vacuum. Every particle you know, protons, electrons, photons, emerges from these fields. They are not objects floating in space. They are excitations of the fields that already exist. When the photon field vibrates, you see light. When the electron field vibrates, you find charge. Matter is not something that fills space. Matter is something space does when its fields ripple. So what is the vacuum? It is the state where none of these ripples are present, but the fields themselves remain. Their potential remains. Their ability to ripple remains. And that potential is enough to create a universe. Think of a perfectly still pond. At first glance, nothing moves. But if the surface is delicate enough, even the quiet brush of wind will create waves. The vacuum is like that sensitive pond. It is ready to ripple the moment conditions allow. This picture becomes even more fascinating when we consider the Higgs field. According to modern physics, the Higgs field permeates all of space. Particles gain mass by interacting with it, but the Higgs field is not always active. According to theory, in the earliest universe before symmetry broke, the Higgs field had a different value, a higher energy configuration. When the field transitioned to its lower energy state, the universe changed in an instant. Particles became massive, forces separated, the rules of nature crystallized, and in that transition, energy was released that helped shape cosmic evolution. This is another example of the vacuum acting like a physical substance, changing states, releasing energy, and giving rise to structure. So when we ask what nothing means in physics, the answer is neither simple nor empty. Nothingness is a field of possibilities. It is a canvas that paints itself. But this leads to an even more subtle idea. The vacuum might not be unique. Different regions of a larger reality may have different vacuum states, each with its own laws of physics. Some vacuum states might produce universes that expand rapidly and cool slowly, like ours. Others might collapse instantly. Others might contain entirely different kinds of particles, forces, or dimensions. If this is true, then our universe is just one stable configuration in a vast landscape of possible vacua. And the nothing from which our universe emerged may simply be one of many background states. In this view, the vacuum is not the absence of existence. It is the foundation of existence, and the questions shift. Instead of asking how something came from nothing, we begin to ask why the vacuum has the properties it does, why its fluctuations are allowed, why its fields can ripple, why its laws take the shape they do. Physics does not yet have those answers, but the clues point toward a universe where emptiness is fertile, where silence contains motion, and where nothingness carries the seeds of everything. And as we gently drift from this chapter, one truth emerges with quiet clarity. The vacuum is not empty. It is the stage on which the universe performs, the canvas beneath all creation, the unseen engine that breathes motion into matter and time. In the next part, we follow that engine backward, asking whether the universe existed in another form before it emerged from the vacuum at all. Part 5. Did the universe exist in another form? Before the Big Bang, some theories suggest that our universe may not be the first. It may be one cycle in an infinite chain of expansions and contractions, each era leaving faint imprints on the next. If so, the Big Bang was not a beginning, but a transition, a page turn in a cosmic book far older than we can imagine. To explore this possibility, we must step into a different rhythm of cosmology, one in which the universe breathes. Instead of beginning once and expanding forever, it expands, slows, contracts, and is reborn. These models are known as cyclic or oscillatory cosmologies, and they shift our perspective from a universe that starts from a singular point to one that moves through endless phases. Each cycle may have its own galaxies, its own stars, its own long arc of time, and our Big Bang might be only one brief spark in that eternal sequence. The idea is ancient. Many cultures imagine the cosmos as a cycle. Hindu cosmology describes vast ages of expansion and destruction. Ancient Greek thinkers spoke of recurring cosmic fires, and early philosophers wondered if the universe rejuvenates itself. Today, modern physics gives these old intuitions new mathematical form. With general relativity, quantum field theory, and models of cosmic inflation, scientists have begun to outline how a universe might contract without collapsing into a singularity and then rebound into a new expansion. One version of this idea is called the Big Bounce. Instead of the universe emerging from an infinitesimal point of infinite density, a singularity, it reaches a minimum size, stabilizes through quantum gravitational effects, and then rebounds outward. Time does not start over. Rather, its direction reverses through a phase transition. Before the bounce, space contracts. After the bounce, it expands. The Big Bang is the moment of reversal, not the first moment of existence. To picture this, imagine a spring gently compressed. As you push inward, the coils grow tighter, but at a certain point, the spring resists further compression. The pressure builds. Eventually, the spring pushes back, releasing energy as it expands. The Big Bounce works in a similar way. The fabric of space-time resists infinite compression, forcing a rebound. The universe begins. Again, not from nothing, but from the remains of its previous state. Quantum gravity, still incomplete but deeply suggestive, offers several mechanisms that could cause such a rebound. In loop quantum cosmology, for instance, space-time itself is quantized into tiny, discrete units. As the universe contracts, these units prevent density from becoming infinite. Instead of collapsing into a singularity, the universe bounces. Time extends both backward and forward. The Big Bang becomes a gateway, not a boundary. Another cyclic idea comes from string theory, the ekpyrotic model. In this view, our universe exists on a three-dimensional brane, floating in a higher dimensional space. Occasionally, another brane drifts close. When the branes collide, the energy released ignites something that looks like a Big Bang, not from infinite density, but from the violent interaction of higher dimensional surfaces. After the collision, the branes separate and drift apart, cooling over billions of years. Eventually, they approach again, triggering another cycle. In this model, each bang is one in a long succession of cosmic encounters. These collisions could even leave subtle patterns in the cosmic microwave background, the faint afterglow of our early universe. Some scientists have searched for hints of asymmetry or circular patterns that might suggest a universe older than our Big Bang. If such patterns exist, they would be like footprints left by previous cycles, ghosts of universes long gone. Yet another model extends inflation theory into eternity. It suggests that while our universe expands and cools, another region elsewhere collapses and rebounds. This leads to a cosmic landscape where universes are constantly being born. Ours might be one bubble among countless others in an ever-changing sea of expansion and contraction. In this view, the Big Bang is not unique. It is one spark in a cosmic storm of creation. But even if cycles exist, would anything survive from one universe into the next? Some theories say no. When the universe contracts, stars collapse, galaxies crumble, atoms break apart, and all structure dissolves into a superheated plasma. When the bounce occurs, that plasma expands and cools, but carries no memory of prior forms. Each universe begins with fresh initial conditions. Other theories, however, allow for faint traces to pass through. In conformal cyclic cosmology, proposed by Sir Roger Penrose, the universe expands so far into the future that particles lose their mass. Black holes evaporate. Eventually, the universe becomes so stretched that distances lose their meaning. Every region becomes geometrically equivalent. In that state, Penrose argues, the universe becomes mathematically similar to the near-singular state of a new Big Bang. One infinitely expanded universe becomes the seed of the next. Remarkably, Penrose has claimed that circular patterns in the cosmic microwave background may be evidence of black hole collisions that occurred in a previous cosmic cycle. These patterns, if real, would be echoes, whispers, from a universe older than our own. But cyclic cosmology raises a deeper philosophical question. If the universe cycles forever, is there a first cycle? Is there a beginning behind the beginnings? Physics does not yet provide a clear answer. Some models suggest infinite cycles, no starting point, only motion. Others suggest cycles must begin after a deeper transition, perhaps from a prior state where even the concept of a universe was undefined. Still, the notion of cycles invites a quiet comfort. It means the cosmos might be part of a larger rhythm, one that persists beyond the death of stars, galaxies, and even space-time itself. It means creation is not a single event, but an ongoing breathing of reality. But to truly grasp whether the universe existed before the Big Bang, we must also consider a subtler idea. Perhaps the universe did not exist as a physical space, but as a set of conditions. Perhaps what existed before the Big Bang was not matter or energy, but a configuration of laws, a state where the vacuum had different values or where the geometry of spacetime was curved differently, a state not recognizable as a universe, but capable of becoming one. This takes us to the quiet edge of scientific speculation. The universe might have existed before the Big Bang, but not in a way we can describe with words like before, after, space, or time. It may have existed in a form beyond our categories, a form that transitioned into our cosmos through a phase change, like water turning into ice. In this view, the Big Bang is not a birth, it is a transformation. Whether that transformation is one instance in a chain of infinite cycles or a unique transition from a prior undefined state remains unknown. But the question itself pushes physics forward. It forces us to ask not only how the universe began, but how reality behaves beyond the limits of time and causality. As we drift gently toward the next chapter, one truth settles quietly. If the universe did exist before the Big Bang, it may not have looked anything like the cosmos we know. It may have been silent or symmetrical or infinitely vast. It may have been shrinking or colliding or transforming. But whatever it was, its imprint lives within us, written into the laws that shaped this era of stars, galaxies, and the small consciousness now wondering about beginnings beyond beginnings. Part 6. The Bounce Model. Could a previous universe have collapsed into ours? In bouncing cosmology, the universe did not emerge from a singularity, but rebounded from a prior collapse. Imagine space compressed to impossible density, then releasing like a spring. In that release, a new universe forms. Here, we trace the slow, inevitable motion that might lead one cosmos to breathe out another. To begin, picture the universe not as a single linear timeline, but as a rhythm, an endless inhalation and exhalation of cosmic structure. Most of us grew up with the image of the Big Bang as an absolute beginning, a point where everything sprang from nothing. But in the bounce model, the Big Bang is not the first act. It is the visible crest of a wave whose troughs lie far beyond our reach. Before the universe expanded, it contracted. Before it grew cool, it heated. Before matter spread outward, it drew inward. And before space-time blossomed into the cosmos we know, it collapsed into a state dense enough to challenge even the imagination of physics. This idea does not erase the Big Bang. It reframes it. The bang becomes the turning point, not the origin. To understand the bounce, we must first follow the universe backward through its current expansion. Today, galaxies drift apart, carried by the stretching of space-time. This expansion is accelerating, driven by dark energy. But if the nature of dark energy changes over cosmic time, and some theories allow for this, its push could weaken. Gravity, weak across intergalactic distances now, might slowly regain influence. Galaxies could begin to drift back together. Clusters could merge. Eventually, the expansion could stall, and the cosmos could begin to contract. This hypothetical contraction is known as the Big Crunch. In classical physics, a contracting universe would end in a catastrophic singularity, an infinitely dense point, the mirror image of the standard Big Bang singularity. But singularities are warnings, not physical realities. They tell us that the equations we use, Einstein's equations of general relativity, are breaking under extreme conditions. Something deeper must take over before infinite density is reached. Quantum gravity, still incomplete, offers hints. According to loop quantum cosmology, space-time is not smooth but granular. It is made of tiny, discrete units, minuscule loops of geometry. As the universe contracts and density increases, these loops resist further compression. Space-time pushes back. Instead of collapsing into a singularity, the universe reaches a minimum size, a smallest possible volume. At that point, quantum pressure becomes enormous, overwhelming gravity's pull, and space-time rebounds. Expansion begins again. This rebound is the Big Bounce. In this view, the Big Bang is not the moment the universe came into existence. It is the moment the contraction reversed direction. Imagine a ball thrown upward. It slows, pauses, and then falls back down. The pause is not the end of its motion, but the turning point. This pause, called the reversal point, is what the bounce represents. A previous universe shrinks, slows, approaches a minimum state, and then expands into the universe we now inhabit. But what did that prior universe look like? Was it like ours, filled with stars and galaxies? Or was it something much stranger? Cyclic cosmology suggests that each universe in the sequence may have similar large-scale properties. But the details, its galaxies, its chemistry, its forms of matter, could differ. When a universe contracts, it heats dramatically. Stars are torn apart, matter dissolves into elementary particles, and space-time becomes turbulent. By the time the bounce occurs, nearly all structure is erased. What survives into the next cycle are not galaxies, but laws, the rules governing space-time, quantum fields, and fundamental particles. In this sense, each bounce is a renewal. Structure is lost, but the blueprint remains. The ekpyrotic model, arising from string theory, offers another form of bounce. Instead of the universe contracting on its own, the bounce is triggered by a collision between higher-dimensional branes. In this picture, our universe exists on a three-dimensional membrane floating in a larger, higher-dimensional space. Another brane parallels ours. Every so often, perhaps every trillion years or longer, the branes drift together. When they collide, the energy released becomes what we observe as the Big Bang. The branes then separate, and the universe expands. Over unimaginable spans of time, they drift again. Another collision occurs. Another universe ignites. This scenario avoids singularities entirely. The bounce is not caused by infinite density, but by geometric interaction. In this model, the previous universe never fully collapses. Instead, it is reshaped by the brane collision. Each universe inherits subtle features, tiny variations in density, slight asymmetries, from the one before. Some scientists have even searched the cosmic microwave background for evidence of pre-bounce structure. The idea is that collisions, distortions, or enormous black hole mergers from a prior era might leave faint circular imprints in the CMB. If such patterns exist, they would be cosmic fossils, surviving through the bounce-like echoes across epochs. So far, results are inconclusive. The universe's earliest light is quiet, nearly flawless. But that quietness, too, fits a bounce story. The contraction phase smooths the universe, erasing irregularities. The bounce, followed by inflation, leaves behind a cosmos remarkably uniform, with only the smallest fluctuations seeding galaxies. If we consider entropy, the measure of disorder, another puzzle arises. How can each cycle begin in a low entropy state if entropy rises across time? Wouldn't each bounce carry more disorder than the last? Some models address this by stretching the universe so much during expansion that entropy becomes diluted across vast reaches of space. When contraction begins again, only a tiny fraction of the expanded universe collapses into the next cycle, effectively resetting entropy. In other models, entropy is shed into extra dimensions during the bounce. These ideas remain speculative, but they share a quiet theme. The universe may not need a beginning. It may simply be part of a larger pattern, one that repeats but never perfectly. Each bounce could alter the constants of nature slightly. Each cycle could drift toward new physics, and each version of the universe might be one iteration in an infinite journey toward complexity. Yet there is something profoundly calming about this perspective. It means the cosmos does not begin in violence but in motion. The bounce is less an explosion and more an exhale, a release of tension built during contraction. A universe dies not in annihilation, but in transformation, and another rises in its wake. This invites a gentle shift in how you think about cosmic origins. Instead of imagining a universe created suddenly from nothing, you imagine a universe transitioning from one state to another, like water freezing or vaporizing. The boundary between cycles is thin, delicate, and governed by laws deeper than classical physics. Still, even if the bounce is real, questions linger. What started the first cycle? Is there a first cycle, or is the idea of first meaningless in an infinite sequence? Some physicists argue that infinite regress, universes emerging from universes, is no more problematic than a single unexplained beginning. Others argue that the bounce itself, being governed by quantum laws, needs no first cause. It simply is. Perhaps the universe has always moved, always breathed, always cycled. Perhaps the bounce is not the exception, but the rule. As we move toward the next chapter, one thought remains with quiet gravity. If our universe was born from the collapse of another, then the Big Bang is not a moment of creation, but a moment of inheritance. And somewhere, deep within the laws that guide our cosmos, may lie the fingerprints of a universe that came before. Part 7. The pre-Big Bang scenario in string theory. String theory suggests that before the Big Bang, the universe may have been a vast, cold, slowly evolving structure, one with dimensions beyond our perception. When two higher dimensional brains collided, the energy of their impact became the fireball we call the Big Bang. In this part, we wander through these hidden dimensions with calm precision. To understand this scenario, we must first soften our intuitions about space itself. The world you move through each day appears to have three spatial dimensions: length, width, and height. You can walk forward, step sideways, or reach upward. These directions feel complete, as if nothing else could exist outside them. Yet, string theory quietly proposes that this familiar space is only part of a much larger structure, like a thin slice of an unimaginably vast loaf of bread. Hidden dimensions may curl beneath every point you see, compact and folded, yet as real as the directions you navigate with your senses. In this deeper landscape, the fundamental constituents of the universe are not particles, but tiny, vibrating strings. Each vibration pattern corresponds to a different particle: photons, electrons, quarks, all emerging not from distinct building blocks, but from different notes, played on the same cosmic instrument. And these strings do not necessarily vibrate in only three dimensions. Their motions may trace paths through additional dimensions that our senses cannot detect. For most of human history, such an idea would have seemed mystical, but in modern theoretical physics, it arises naturally from the mathematics that attempt to unify the forces of nature. In this expanded view, our universe resides on a three-dimensional brane, a higher dimensional surface floating within a larger region known as the bulk. Imagine a soap film drifting inside a vast invisible room. That film is our universe. It has its own internal physics, its own laws, its own galaxies drawn on its surface. Meanwhile, other films, other brains, may drift nearby, parallel but separate, like silent neighboring worlds that never intersect. Most of the time, these brains are cold, quiescent, and almost perfectly still. But in the pre-Big Bang scenario, stillness does not last forever. Brains move, they fluctuate, they respond to forces we cannot perceive, slowly shifting over stretches of time so immense that human history seems like the flicker of a match in the void. And according to some versions of string theory, the Big Bang may have occurred when our brain collided with another. This collision released enormous amounts of energy, enough to heat the universe into the dense, glowing plasma from which all matter eventually formed. In this picture, the Big Bang is not an origin point, it is an impact. This idea belongs to a family of theories known as ekpyrotic and cyclic models, which reimagine the birth of our cosmos as the aftermath of events in higher dimensional space. In these models, the universe before the Bang was not a point of infinite density, but a vast stretch of cold, nearly static space on a brane. Matter had not yet formed, light had not yet scattered. There were no particles, no stars, no quantum froth, only fields, only geometry, only potential. The collision injected heat and motion into this quiet structure. It ignited the expansion we now call the Big Bang. But instead of coming from a singularity, the fireball came from kinetic energy, energy stored in the slow drift of branes across cosmic distances. This framework helps answer one of cosmology's greatest puzzles. Why is the universe so uniform on large scales? Distant regions of the cosmos, separated by billions of light years, have nearly identical temperatures. Standard Big Bang cosmology struggles to explain this without invoking inflation, a brief period of exponential expansion. But in ekpyrotic models, the long, slow evolution before the collision smooths the brane. Over vast periods of time, irregularities shrink, energy dissipates, and everything evens out. The brane becomes exquisitely uniform, like a sheet stretched taut. When the brane collides, it transfers that uniformity into the newborn universe. But this does not mean the early universe was perfectly smooth. Small ripples existed, tiny variations that were amplified into galaxies, stars, and planets. Interestingly, ekpyrotic models generate these ripples through the geometry of the branes themselves. As they approach each other, their shapes subtly distort, creating regions of slightly higher or lower energy density. These become the seeds of cosmic structure. In this way, the shapes of universes may be sculpted by the wrinkles in higher dimensions. It is a quiet idea, a cosmos shaped not by chaos but by geometry. Still, this raises a profound question. If the Big Bang was caused by a collision, what existed before the collision? In some models, the branes drift eternally in the bulk, colliding every trillion years. After each collision, a universe forms, expands, cools, and eventually becomes cold and empty. Then, the branes drift again, slowly drawn toward each other by a gentle higher dimensional force. Another collision occurs. Another universe ignites. In this sense, the universe may not only have existed before the Big Bang, it may have existed through countless cycles of brane encounters. Not cycles of contraction and expansion within a single universe, as in the bounce model, but cycles of contact between separate spatial surfaces. Each collision births new matter. Each separation allows matter to cool. Each return sets the stage for a new era of cosmic light. If this is true, the universe is not a single book, but a library, each collision writing a new volume on the same enduring branes. Yet, string theory does more than propose brane collisions. It suggests that the pre-Big Bang universe may have had entirely different physics. For example, the strength of forces, the mass of particles, and the shape of space might differ before the collision. What we identify as constants, unchanging numbers that define nature, could shift between cycles. This means the laws of our universe may be fossil imprints of the conditions that existed on the branes before the Bang. Some physicists have explored whether the signature of this pre-Big Bang era could appear in the cosmic microwave background. Certain patterns, non-Gaussian fluctuations, directional alignments, or specific modes of polarization might reflect the geometry of brane motion or brane shape before impact. No conclusive evidence yet exists, but the possibility remains open. In a sense, the oldest light we can detect might carry a memory of a time before time. The pre-Big Bang scenario also carries a soft philosophical shift. It tells us that the universe does not need to begin in a moment of infinite density, a place where our mathematics fail. Instead, it can begin in a moment of contact, a moment where two cold, calm worlds touch. The violence of the Big Bang becomes the aftershock of a gentle, cosmic drift. That drift invites wonder. It suggests that the universe existed long before the light of the Big Bang reached us. It suggests that the deep, quiet phase before our universe was not empty or meaningless. It was simply different, a slow, cold evolution in dimensions our minds struggle to imagine. And it suggests that the Big Bang was not a creation event, but a transformation, one phase of a deeper, multidimensional story. As we move onward, we carry this gentle idea. If the universe began in a collision, then before the fireball, there was form, there was motion, there was geometry, there was a quiet, higher dimensional prelude. And somewhere, deep within the mathematics of string theory, the echoes of that prelude may still be shimmering, waiting softly for us to hear them. Part 8. Eternal Inflation, a cosmos that never truly began. Inflation theory, extended far beyond its original purpose, paints a universe where new regions of space continually blossom from older ones. In this picture, our Big Bang was just one bubble forming in an endless sea of inflation. There was no beginning, only perpetual creation in every direction. To enter this view, let your mind drift toward the edge of the observable universe, the farthest frontier we can see. Beyond that horizon, light has not yet reached us. Beyond that, space continues. And beyond that, further still, stretch regions of the cosmos that inflation theory suggests may be expanding faster than light, too distant to ever be observed. In these regions, inflation does not end. It continues, restless and relentless, transforming the universe into a vast, ever-growing mosaic of cosmic domains. This idea begins with ordinary inflation, a phase of rapid expansion in the first tiny fraction of a second after the Big Bang. Inflation was introduced to explain why the universe looks so smooth on large scales, why distant parts share the same temperature, and why space appears nearly flat. But once the mathematics were written down, something surprising emerged. Inflation need not stop everywhere at once. In fact, in many models, it cannot stop everywhere at once. Even as inflation ends in one region, allowing a bubble universe to form, it continues in other regions. Those regions stretch and grow, spawning new pockets of space where inflation eventually ends again. Each of these pockets becomes its own universe, with its own Big Bang, its own expansion, and possibly its own physical laws. Our universe, then, becomes one bubble in a frothing infinite ocean. This concept is known as eternal inflation, and it carries a quiet yet profound implication. If inflation never stops across the larger multiverse, then there was never a first bubble, never a first region where inflation began. The cosmos does not trace back to a single moment. It simply stretches backward without end, like an infinite landscape where creation is always happening somewhere. To visualize this, imagine boiling water. Each bubble forms, grows, and rises, but the water beneath continues to simmer. New bubbles appear constantly. No single bubble is the first. No single bubble is the last. The process has no preferred moment. Now, imagine each of those bubbles is a universe, expanding from its own Big Bang. The water is the inflating medium, a state of space with enormous energy density expanding exponentially. In some regions, bubbles appear. In others, inflation continues undisturbed. The boiling never stops. And in this picture, existence has no starting point. But this cosmic boiling is not chaotic. It follows precise rules written into the physics of quantum fields. The inflaton field, the field responsible for inflation, has a landscape of possible values. In some regions, the value rolls downhill, ending inflation and releasing energy into matter and radiation. In other regions, random quantum fluctuations push the field uphill, sustaining inflation indefinitely. This interplay between downward flow and upward fluctuation makes eternal inflation not just possible, but natural. Some regions of space will always contain conditions where inflation persists. This raises one of the deepest questions in cosmology. If our Big Bang was only a local event in a much larger, eternally inflating space, what lies beyond our cosmological horizon? Is the larger structure finite or infinite? Does inflation stretch forever, spawning universes endlessly, or does it cycle in patterns we cannot yet detect? Mathematically, eternal inflation produces an infinite amount of space in finite time. even as individual bubble universes form, the inflating regions grow faster than they are consumed. The larger cosmos becomes a fractal, an endlessly repeating pattern at every scale, where pockets of non-inflating space nest within vast expanses of inflating space. This fractal nature carries a serene, almost meditative beauty. The multiverse is not chaotic but patterned, endlessly generating variety through simple rules. In each bubble universe, inflation ends, and something like the Big Bang unfolds. Heat, expansion, particle formation, galaxies taking shape. But each bubble may cool into a universe with different constants. One universe may have stronger gravity, causing stars to burn quickly. Another may have weaker forces, preventing atoms from forming at all. Some bubbles may be barren, others may be fertile, nurturing galaxies, planets, life, and perhaps minds capable of wondering about the infinite sea from which they emerged. Our universe drifts among them, one luminous bubble in an endless, silent expanse of creation. If eternal inflation is correct, then our observable universe, the part we can measure, is only a tiny patch in a vastly larger structure. The 93 billion light-year sphere we can see is small compared to the regions still inflating beyond our reach. Time itself becomes local. What we call the age of the universe, 13.8 billion years, is merely the age since inflation ended in our bubble. But inflation may have been happening long before our bubble existed. It may still be happening, and it may continue forever. This perspective quietly dissolves the idea of a cosmic beginning. In an eternally inflating multiverse, creation has no privileged moment, no single genesis point. The boundary between before and after becomes fuzzy, because there is always some region where inflation is active and always some region where it is ended. Even asking, when did everything begin, becomes subtle. The answer depends on which bubble you inhabit. But can we find evidence of other bubbles? Could the cosmic microwave background contain scars from collisions between our universe and others? Some cosmologists have suggested that if two bubble universes bumped into each other, the collision could leave a circular imprint, a subtle disruption in the temperature map of the sky. Searches for these signatures have been conducted, and while no definitive detection has been made, the possibility remains. If such a pattern were found, it would be a whisper from beyond our bubble, a sign that our universe brushed against another in the distant past. Even without direct evidence, eternal inflation offers elegant explanations for several puzzles. It helps explain why physical constants appear fine-tuned for life. In a multiverse with countless bubbles, most universes will not support structure. We inhabit a universe where the constants allow atoms, stars, and biology simply because those are the conditions in which observers can exist. This is not a claim of purpose, only selection. If countless universes exist, we naturally find ourselves in one where the conditions allow beings capable of noticing them. Eternal inflation also reframes the question of what existed before the Big Bang. Instead of seeking a singular origin, we are invited to imagine a vast, timeless tapestry, a cosmos where new universes continuously bud from inflating space. Our Big Bang becomes one moment in a ceaseless process. Even the word before becomes delicate, because the multiverse does not share a common time. Each bubble has its own clock, its own arrow of time, its own beginning. From this view, the question, what happened before the Big Bang, transforms. The answer may be that before our Big Bang, inflation was happening elsewhere, and before that, it was happening elsewhere again. The story stretches backward without end, like a horizon that recedes as you walk toward it. As we conclude this chapter, one thought rests quietly in the background. If eternal inflation is correct, then the cosmos never needed a beginning. It has always been growing, blooming silently, endlessly, beautifully. And somewhere, beyond the reach of any telescope, new universes are forming right now, expanding into existence like soft sparks in an infinite night. In the next part, we drift into the possibility that not only do other universes exist, but that ours may be just one among an immeasurable family, a multiverse bound not by borders, but by the quiet rules of creation itself. apart. 9. The multiverse. If our universe has siblings. If inflation is eternal, then countless universes may exist beyond our cosmic horizon, each with its own physical laws. Some may be stillborn, some brief flickers, and some stable like ours. In this quiet chapter, we explore the idea that the pre-Big Bang state may have been a parent multiverse, a silent nursery of worlds. To open this idea gently, imagine standing on a shore at night, looking out at a vast ocean. You see only the waves nearest to you, lit faintly by the moon. But you know the ocean does not end there. It stretches far beyond your vision, wave after wave, each shaped by the same laws of physics yet distinct in its precise motion. In the multiverse picture, our universe is one such wave, luminous, intricate, yet only one small part of a much larger expanse. That expanse may contain countless other bubbles of space-time, universes forming, inflating, cooling, and evolving. Most will never meet, just as waves far apart on an ocean never collide. Light from one bubble will never reach another. Each forms its own enclosed reality. In our bubble, we see stars, galaxies, the cosmic microwave background. But beyond the border where our light stops, other universes may drift quietly, unaware of us, and forever out of our reach. The idea of the multiverse arises naturally from eternal inflation. Once inflation begins, the mathematics show it will not stop everywhere. Even after it ends within a region, producing a universe like ours, it continues in other regions. In those regions, more universes form. And so the process repeats without end. The multiverse becomes not an optional concept, but a consequence of inflation's structure. This invites a delicate but profound shift. The Big Bang may not have been the beginning of all things. It may have been the beginning of our universe, but not the origin of existence itself. Instead, it may be one moment in a landscape where creation is ongoing, where cosmos after cosmos flickers into being. If this is true, the pre-Big Bang state of our universe might not have been emptiness at all. It may have been a larger inflating background, a cosmic field giving birth to universes the way a tree produces leaves in spring. Each leaf is distinct with its own patterns, but all arise from the same deeper structure. One of the most intriguing aspects of the multiverse is the idea that each universe can have different physical laws. In our universe, the strength of gravity, the charge of the electron, the speed of light, all are constants that seem finely tuned for complexity. A tiny change in these values could render stars impossible, atoms unstable, or chemistry too fragile for life. This extraordinary sensitivity would be mysterious in a single universe picture. But in a multiverse picture, it becomes less surprising. If countless universes form with different constants, we find ourselves in one where complexity is possible simply because we could not exist in universes where it wasn't. This is known as the anthropic principle, not a claim of purpose or design, but a simple recognition that observers can only arise in universes capable of supporting observers. Still, the multiverse may hold universes far stranger than ours. Some may freeze instantly, their physical laws preventing heat from spreading. Some may expand so rapidly that matter never clumps into stars. Some may collapse moments after forming, becoming black holes instead of galaxies. Some may have more dimensions than ours, or different kinds of particles, or entirely unfamiliar physics. And some may be stable and long-lived, with galaxies and planets of their own, perhaps even life of their own. If the multiverse exists, then the variety of creation is almost unimaginable. But this variety is not chaotic. It emerges from the structure of the inflaton field, the geometry of the vacuum, and the quantum rules that govern high-energy physics. Creation becomes not a singular event, but a natural process, like seeds sprouting in a vast cosmic meadow. One question often arises: can universes within the multiverse interact? Could they collide or influence each other? In most models, the bubbles expand rapidly, forming horizons that separate them permanently. But under certain conditions, especially early in their formation, bubbles could collide, leaving faint marks in one another's cosmic microwave backgrounds. Some cosmologists have searched for these circular imprints, ghost-like scars that might reveal where our universe brushed against another long ago. So far, no conclusive evidence has been found, but the possibility remains that the sky above us contains the faintest memory of another universe. Another version of the multiverse arises from string theory's landscape of possible vacuum states. String theory predicts an enormous number of possible configurations, perhaps 10 to the power 500 or more, each with its own laws of physics. If the universe can take on any of these configurations, then the multiverse becomes not just a set of spatial bubbles, but a vast array of possible realities. Inflation might move the universe between these states, like a traveler wandering through a landscape of valleys and peaks. Each valley corresponds to a stable universe with its own unique physics. Our universe sits in one valley in this landscape, but countless others may exist elsewhere. In this picture, the multiverse is not a physical ocean, but a landscape of possibilities. Our universe is one realization among endless potential worlds. Some physicists go even further, proposing quantum multiverses arising from the many worlds interpretation of quantum mechanics. In this interpretation, every quantum event with multiple possible outcomes leads to branching universes, each representing a different outcome. These universes do not arise from spatial inflation, but from the unfolding of quantum possibilities. In this view, a multiverse is not only spatial, but temporal and probabilistic, a fractal of realities emerging from every measurement. These models differ in their mechanisms, but they share a quiet unity: the idea that our universe is not alone. If the multiverse exists, the pre-Big Bang state becomes easier to imagine. Before our universe existed, inflation was happening somewhere. Before that, other universes were forming. Before those, still others. The chain stretches back not to a single origin, but to an eternal process. The question, what came before, becomes soft, like asking what came before the first wave in an infinite ocean. The answer may be that there was no first wave. There is only the ocean, endlessly making waves. Yet the majesty of the multiverse does not diminish the uniqueness of our universe. Instead, it casts our world in a new light. We are a particular combination of constants, dimensions, and fields, a particular expression of cosmic possibility. One bubble that cooled just right, expanded just right, and formed galaxies with the quiet regularity needed for life to emerge. In a multiverse, the rarity of such a universe does not diminish its beauty. It amplifies it. And so as we drift to the end of this chapter, we hold the idea gently. Our universe may be one among many, but it is uniquely ours, shaped by the quiet inheritance of a larger reality we may never see. In the next part, we turn toward the deepest frontier of all, the realm where space-time breaks down and the question of before becomes tangled with the quantum fabric of existence itself. Part 10. The Role of Quantum Gravity, where space and time break down. As we approach the earliest possible moment, the familiar equations of physics begin to contradict each other. Space becomes grainy, time loses meaning, and the universe becomes a foaming quantum sea. In this segment, we explore the strange landscape where general relativity and quantum mechanics meet and fail. To understand this frontier, imagine peeling back the layers of the universe like layers of sedimentary rock. Each layer represents a different scale. At the surface lies the everyday world. Apples falling, planets orbiting, clocks keeping steady time. These are governed by Einstein's general relativity, a theory of smooth space-time that bends gently under the influence of matter and energy. Dig deeper, and you encounter the atomic world, where electrons smear into probability clouds and particles behave like both waves and points. This is the realm of quantum mechanics, a theory that thrives in chaos and uncertainty. Both theories describe their domains beautifully. Both have been tested countless times, yet they refuse to speak to each other. General relativity insists that spacetime is continuous, malleable, and geometric. Quantum mechanics insists that everything, including energy, momentum, and fields, comes in discrete packets. When you push these theories into the same territory, into places where gravity is strong and scales are small, they clash. The mathematics breaks. Predictions become nonsensical. At the core of a black hole, at the very beginning of the universe, the two pillars of physics contradict one another completely. These contradictions are not a trivial inconvenience. They signal that our understanding of reality is incomplete. At extremely small scales, the universe reaches what physicists call the Planck length, about 10 to 35 meters. This is a scale so tiny that if an atom were expanded to the size of the observable universe, a Planck length region inside it would still be smaller than a dust mote. At this scale, space-time cannot remain smooth. Quantum fluctuations distort the geometry itself, making space flicker and twist. Instead of a continuous fabric, space-time becomes lumpy, like a foam of tiny bubbles constantly appearing and vanishing. This quantum foam, first proposed by John Wheeler, is a metaphor for the turbulence of space-time at the Planck scale. Every point becomes unpredictable. Distances lose meaning. The notion of before and after dissolves because time itself becomes unstable. In such a landscape, the equations of relativity fail. They cannot handle such violent granular behavior. Quantum mechanics also fails because it cannot describe the geometry that underlies its own probabilities. What emerges is the need for a new theory: quantum gravity. Quantum gravity is not a single idea, but a collection of attempts to unify the smooth geometry of relativity with the probabilistic nature of quantum mechanics. These attempts are among the most ambitious in science, not because they are speculative, but because they demand a new language for reality itself. And though we do not yet have a full theory of quantum gravity, several promising frameworks offer glimpses of what the universe might have been like before time stabilized into the orderly flow we experience. One such framework is string theory, which suggests that space-time is not fundamental at all. Instead, it emerges from the behavior of tiny one-dimensional strings vibrating in a higher dimensional space. At the Planck scale, these strings do not obey the smooth rules of relativity. They vibrate, split, and reconnect, giving rise to forces and particles, including gravity. In this view, the quantum foam is not chaos but a sea of strings interacting in ways too complex for classical physics to describe. Another approach is loop quantum gravity, which proposes directly that space-time is quantized. According to this view, space is composed of tiny loops woven into a vast network, like a fabric knit from discrete threads. These loops are unimaginably small, but they have real, measurable properties. They define the smallest possible units of area and volume. At large scales, this network appears smooth, just as a woven cloth appears continuous from a distance. But at the Planck scale, the granularity becomes undeniable. In loop quantum gravity, the Big Bang is not a singularity. It is the moment when space-time transitions from a contracting phase to an expanding phase, a bounce. This transition is made possible because the loops resist compression beyond a certain limit. They provide a quantum repulsion that prevents infinite density. Time does not start at the bang, it simply changes direction. There are other ideas as well. Causal dynamical triangulations, where space-time is built from tiny triangular building blocks. Asymptotically safe gravity, which suggests gravity becomes well-behaved at high energies. Holographic theories, which propose that our three-dimensional reality is encoded on a two-dimensional surface. These models differ in detail, but they share one key insight: space and time are not fundamental features of reality. They emerge from something deeper. This realization reshapes our understanding of the pre-Big Bang universe. If space-time itself is emergent, then the question, what happened before the Big Bang, may not refer to a temporal before at all. Instead, the Big Bang might mark the boundary between two phases of an underlying quantum system. What lies beyond the boundary may not be describable in terms of time or space because those concepts had not yet crystallized. In the absence of space, there is no distance. In the absence of time, there is no sequence. What remains is something more primitive, a quantum gravitational state whose behavior we can only begin to infer. It is a state where geometry fluctuates wildly, where energy densities are immense, where matter as we know it cannot exist, where causality, the idea that one event follows another, breaks down. The universe becomes a storm of probabilities, a sea of potentialities waiting for the right conditions to settle into order. When the universe expanded and cooled, these quantum fluctuations averaged out, geometry smoothed, time emerged, space unfolded, particles gained mass, forces differentiated. Physics as we know it awakened from the whirlwind. This moment, the transition from quantum gravity to classical spacetime, is what we call the Big Bang. Not a singular explosion, but a symmetry breaking, a phase transition, the universe passing from a timeless state to a temporal one. To sense this transition, imagine a pane of glass cooling from molten liquid. At high temperatures, molecules move chaotically. There is no rigid structure, but as the glass cools, the molecules settle into a stable arrangement. A familiar solid emerges. The structure is new, not because the molecules appeared from nowhere, but because their pattern shifted. Quantum gravity suggests something similar happened to spacetime. Before the Big Bang, spacetime was fluid and unstable. After the Big Bang, it became rigid enough to support the laws of physics we recognize. Time began to flow with a steady rhythm. Space expanded, structure formed. This does not mean the pre-Big Bang universe was chaotic in a destructive sense. Instead, it was a realm where classical ideas do not apply, a place where questions like where and when lose coherence, a place that may hold the answers to our deepest questions, but in a language we have not yet learned to speak. As we drift to the end of this chapter, one truth becomes clear. To understand what came before the Big Bang, we must understand the universe before space-time existed. That journey leads us into quantum gravity, a frontier where our concepts of reality dissolve and where the seeds of our universe were sown in silence. In the next segment, we explore a radical possibility arising from this frontier, that black holes themselves may be gateways to new universes, each carrying the imprint of the quantum fabric that gave birth to ours. Part 11. Could black holes give birth to new universes? Some scientists propose that every black hole might contain a new universe within it, sealed off by the event horizon. If so, our own universe could have been born inside a black hole in another cosmos. In this part, we follow the geometry of spacetime inward toward the possibility of cosmic ancestry. To begin this quiet exploration, imagine hovering at the edge of a black hole, the event horizon, a boundary so absolute that even light cannot escape. From the outside, it appears serene, almost deceptively calm. No violent flashes, no dramatic spirals of light within the horizon itself. But crossing that invisible threshold would be like stepping off the edge of our world into a region where the rules of space and time fold into unfamiliar shapes. In that folding, some physicists believe, lies the seed of creation. Black holes are often described as the endpoints of massive stars, collapsing under the weight of their own gravity. But the true nature of their interiors remains hidden behind the event horizon, protected from our observations by the very geometry of spacetime. General relativity predicts that once inside, matter collapses toward a singularity, a point of infinite density where time itself ends. Yet, singularities, like the Big Bang singularity, signal not physical reality, but the breakdown of our theories. They are signs that quantum gravity must take over. And when quantum gravity enters the picture, new possibilities emerge, possibilities that transform black holes from cosmic tombs into cosmic wombs. One such possibility comes from the idea that inside each black hole, spacetime may continue, not collapse. Instead of a singularity, the intense compression of matter could trigger a bounce, similar to what some bouncing cosmologies propose for the universe at large. In this scenario, the interior of a black hole pinches off from our universe and inflates into a new space-time region. The result is a baby universe connected to its parent by a wormhole-like structure that quickly seals itself off. From the outside, the black hole remains a black hole. But from the inside, the black hole becomes a cosmos expanding from its own Big Bang. This idea is not merely poetic. It emerges naturally from attempts to reconcile general relativity and quantum mechanics. In Einstein's equations, certain solutions describe wormholes, tunnels through spacetime that link one region to another. These solutions are usually unstable, but quantum corrections could stabilize them briefly, allowing a black hole interior to bud off into a new universe. In this view, the universe itself could have been born inside a black hole in a parent universe. Time in the parent universe flows toward the black hole's center. But inside, a new timeline unfolds outward, its own expanding space, its own laws, its own cosmic evolution. This raises a profound question. If universes can form inside black holes, what determines the physics of the baby universe? One answer comes from the idea of cosmic natural selection proposed by physicist Lee Smolin. According to Smolin's theory, each black hole gives rise to a new universe with slightly altered physical constants. In this evolutionary landscape, universes that produce many black holes become more common over time because black holes have more opportunities to create descendant universes. Over countless cosmic generations, parameters such as the strength of gravity or the mass of particles drift toward values that maximize black hole production. In this framework, our universe is not random. Its laws may be fine-tuned to favor the formation of stars that collapse into black holes, and the delicate balance of physics that allows stars, planets, and life could be a byproduct of a deeper evolutionary process that spans multiple universes. But even without this evolutionary angle, the notion of black hole universes carries a quiet elegance. The environments inside black holes are incredibly similar, in some ways, to the conditions of the early Big Bang. Both involve extreme density, intense curvature of spacetime, and energies high enough to reshape matter fundamentally. If these environments naturally lead to expansion under quantum gravity, it becomes less surprising that black holes could seed universes. Another intriguing perspective arises from loop quantum gravity. In some models, the singularity inside a black hole is replaced by a quantum bounce. Instead of collapsing to infinite density, matter reaches a minimum size and then expands into a new region of spacetime. From the outside, the black hole behaves normally, but inside, the geometry stretches open into a new universe. If this is correct, then the interior of every black hole contains a complete, separate cosmos, causally disconnected from our own. These baby universes might have different arrows of time. Their timelines could begin where ours seem to end. And while nothing from inside the baby universe can return to the parent universe, the child universe inherits its geometry from the collapse that created it. The mass of the black hole, the spin, the distribution of the collapsing matter, these may imprint subtle initial conditions on the baby universe, just as the details of the bounce shape the earliest moments of cosmic inflation. Some physicists have taken this idea even further. They propose that the Big Bang itself may be mathematically identical to the interior of a black hole. Not metaphorically, the equations describing the horizon of a black hole and the surface of the Big Bang share deep structural similarities. Both mark boundaries where time behaves strangely. Both involve regions where classical physics fails. Both require quantum gravity to understand what lies beyond. It is possible that what we call the Big Bang was not the beginning of everything, but the moment our universe emerged through the inner horizon of a black hole in another universe. That universe could be larger, older, and governed by similar or different laws. Our universe, in turn, may sprout black holes that give rise to new universes, continuing an endless branching tree of cosmic ancestry. Imagine a fractal of universes, each black hole a seed, each seed a new cosmos, each cosmos producing more seeds. Reality becomes a vast, interconnected forest, but one where no branch can see or touch the others. Each universe lives its life sealed from the rest, yet connected by a chain of descent. This perspective shifts our place in the cosmos. Instead of asking, what came before the universe, we begin asking, what universe came before ours? Instead of imagining a single moment of creation, we imagine a lineage. Our universe becomes a child born from a collapse, and the black holes within our universe may, even now, be giving birth to new universes of their own. This idea carries a quiet humility. It tells us that our cosmos may not be the defining structure of reality, but a single bloom in a garden of unimaginable scale. Each universe grows from the collapse of structure in its parent universe. Each contains worlds that rise and fall, stars that ignite and die, black holes that open into new realms. If this picture is true, the multiverse is not a random collection of bubbles, but a branching genealogical tree, a cosmic family where ancestry is traced not through DNA, but through space-time curvature. Yet this notion, as beautiful as it is, remains speculative. We cannot observe inside a black hole. We cannot see the birth of a baby universe, but the mathematics whispers the possibility. And the silence around black holes, the perfect, impenetrable horizon, invites contemplation of what might lie beyond. As we close this chapter, one soft thought remains. The universe may not be a singular miracle. It may be one generation in a long cosmic lineage, each universe giving birth to the next in quiet, unseen moments of collapse. And somewhere, deep within the fabric of our own universe, new universes may already be unfolding, hidden inside the darkness of black holes. In the next chapter, we turn to ancient echoes, ideas from myth and early philosophy that astonishingly mirror the modern scientific search for origins, and how those old stories may hold symbolic clues to the cycles we now investigate. Part 12. The Cosmic Egg, Ancient Ideas That Echo. Modern Cosmology. Long before physics, many cultures imagined the universe beginning inside a primordial egg, a silent sphere holding potential. Surprisingly, modern models like the singularity and the inflaton field carry echoes of this ancient metaphor. Here, we examine how myth and physics converge in the search for origins. When ancient civilizations looked into the night sky, they did not see a void. They saw a story unfolding, a quiet cosmic narrative waiting to be deciphered. Before telescopes, before equations, before the notion of space-time existed, many cultures imagined the universe emerging from a sealed, radiant shell. This cosmic egg appeared in Hindu cosmology, in Greek Orphic tradition, in Chinese creation tales, in Finnish mythology, and in countless oral cultures whose voices are now quiet with time. These eggs were not simply symbols of birth. They were metaphors for confinement, for potential, for a universe waiting to unfold. Inside the egg, everything that would ever exist was held in a single, timeless state. Outside, there was silence. Creation was not an event, it was a hatching. What makes this motif so striking is not its poetic beauty, but its uncanny resonance with modern cosmology. The early universe, especially in its first unimaginably small fraction of a second, behaved in ways that mirror these ancient images. A hot, dense state, a boundary separating inside from outside, a transition where potential becomes reality. To trace this connection calmly, we must first return to the physics. Modern cosmology tells us that the universe began in a state of extreme density and temperature. Whether this state was a singularity, an inflaton field, a quantum tunneling event, or a remnant of a prior universe, it shared one defining characteristic. It contained within it everything that would become our cosmos. Every galaxy, every star, every atom, every future moment of time. All of it was compressed into a form where its separate identities had not yet emerged. This early state was not a place with structure or shape. It was a condition. It was a potential waiting to expand, to cool, to differentiate. It was, in a sense, an egg, not a literal shell, but a boundary between the unformed and the formed. Ancient myths, though unscientific by design, captured the emotional truth of this boundary. Consider the Orphic egg of Greek mythology, a radiant sphere encircled by a serpent containing the god Phanes, the bringer of light. When the egg cracked open, light spread outward, and the ordered cosmos took shape. Or the Hindu Brahmanda, the golden cosmic egg from which Brahma emerged, bringing forth time, space, and matter. or the Chinese cosmic egg of Pangu, in which heaven and earth were fused until a being grew within, separating light and darkness. These stories do not describe physics, but they describe feeling, the feeling of a universe hidden in silence, waiting for the moment of unfolding. Modern physics often begins with abstraction, with equations that seem cold and distant, yet the early universe behaves in ways that echo the intuitions of ancient mythmakers. For instance, during cosmic inflation, a brief period of exponential expansion, the universe was dominated by the inflaton field, a smooth, high-energy state that filled all of space. This field behaved like a sealed environment, maintaining a uniform temperature and pressure until subtle fluctuations allowed it to decay, releasing energy and igniting the Big Bang as we understand it. The inflaton field acted like a cosmic egg, uniform, sealed, featureless, yet brimming with potential. Its decay was the hatching. Even the singularity concept, despite being incomplete, resembles the ancient idea of compression. A point with infinite density is a mathematical way of expressing that the universe was once confined to a state beyond ordinary comprehension. Just as myth speaks of a world before world compressed into an egg, physics speaks of space-time compressed into a condition where classical laws cease to apply. Another echo comes from the notion of symmetry breaking. Before the universe cooled, all forces may have been unified. There was no distinction between gravity, electromagnetism, and the nuclear forces. Everything was one. But as the universe expanded and cooled, these forces separated. Structure appeared, particles gained mass, interactions diversified. Myth speaks of heaven separating from earth, of light dividing from darkness, of order emerging from chaos. Physics speaks of phase transitions, but both describe the same idea: differentiation from unity. This shared structure does not imply ancient people understood quantum fields. Instead, it suggests something deeper. The human mind, when faced with the mystery of existence, reaches for metaphors that capture the transformation from potential to actuality. And physics, though it uses different tools, seeks answers to the same questions. Where did everything come from? What was the state before structure existed? What force brought order? One might imagine the cosmic egg as a metaphor for a field so uniform that it had no features, waiting for a symmetry to break. One might imagine the cracking of the egg as analogous to inflation ending, releasing a burst of energy. One might imagine the shell as the boundary between a prior state and the space-time we inhabit. Even quantum tunneling models echo myth. In these models, the universe arises from a quantum fluctuation crossing a potential barrier, a transition from nothing to something. The universe is not created from emptiness, but from a probabilistic sea of possibilities. The moment of tunneling acts like the egg cracking, sudden, irreversible, transformative. But perhaps the richest connection comes from the idea that the universe once existed in a state where time itself had no direction, a timeless, homogeneous condition. In many myths, creation begins not in a sequence, but in timelessness. The cosmic egg floats in a void where time does not yet flow. Only when the egg opens does time begin. Physics proposes something remarkably similar. At the earliest scales, time may not have existed as we know it. Quantum gravity suggests that time may emerge from a deeper, timeless state. In such a state, asking what happened before becomes meaningless. Before the egg hatches, there is no before. There is only potential. Ancient myths captured this intuitively. Modern physics captures it mathematically. What these parallels reveal is not that myth predicted science, but that science and myth both seek to describe transitions that lie beyond ordinary perception. Myths use narrative. Physics uses mathematics. But both gesture toward a boundary between nothing and everything. Still, the differences are as important as the similarities. Ancient myths often involve intent, a deity or being causing creation. Modern cosmology seeks mechanisms, not intentions. It searches for laws, not storytellers. The cosmic egg in physics is not laid by anyone. It arises from fields, equations, or prior universes. The unfolding is not guided by consciousness, but by physical necessity. Yet both approaches convey awe. Both ask us to imagine a universe hidden inside something smaller than imagination, then breaking open into the vastness we now inhabit. As we drift toward the end of this chapter, a soft reflection lingers. Perhaps the oldest stories and the newest theories share a language of transformation. Whether told through mythic eggs or quantum fields, the origin of the universe is framed as a passage from stillness to motion, from potential to reality, from silence to light. In the next segment, we explore another deep connection, the idea that time itself may be cyclic, echoing not only ancient narratives, but also the rhythms found in quantum cosmology. Part 13. Was there ever truly a singular moment? The singularity, the infinitely dense point from which the universe expanded, may not be real. Instead, it might be a sign that our equations are incomplete. In this chapter, we ask whether the universe truly began at a single point or whether that point is an artifact of our limited understanding. To explore this question gently, imagine tracing the history of the cosmos backward. Galaxies move closer, clusters tighten, matter compresses, temperatures rise. Eventually, everything converges toward an unimaginably small region. As we retrace this cosmic contraction through Einstein's equations, space-time curves more and more sharply until the numbers explode into infinities. Density becomes infinite, temperature becomes infinite, curvature becomes infinite. The equations cease to describe a physical world. Instead, they point to a boundary, a place where our mathematical map stops. This boundary is what we call the singularity. But does the singularity represent an actual state of the universe? Or is it a signpost marking the point where our theories no longer apply? Most physicists now believe the latter. Singularities are not physical objects. They are symptoms. They appear in our equations when we use tools that are not meant for extreme conditions. It is like trying to navigate deep ocean trenches with a map drawn for shallow coastal waters. When you push a theory beyond its domain of validity, it produces results that do not make sense. The singularity is a signal, a quiet warning that a new theory is required. In this way, the Big Bang singularity resembles the singularity predicted at the center of a black hole. In both cases, general relativity predicts a point where density goes to infinity. And in both cases, physicists believe that quantum mechanics must intervene to resolve the breakdown. Singularities are clues that our understanding of space-time is incomplete. But if the singularity is not real, what actually happened in the earliest moment of the universe? To answer this, we must explore how time, space, and geometry behave in extreme conditions. At familiar scales, space-time is smooth and continuous, but as we approach the Planck length, 10⁻35 meters, the smoothness dissolves. Quantum fluctuations become so intense that space-time foams and bubbles. The concept of distance becomes fuzzy. The idea of a point loses meaning, and the equations of relativity, which assume smoothness, collapse. In this chaotic regime, a new theory, quantum gravity, is needed. And although we do not yet have a complete theory, several promising frameworks suggest that the singularity may be an illusion caused by extrapolating classical physics into a region where quantum behavior dominates. One such framework is loop quantum cosmology. In this model, the fabric of space is woven from tiny loops, each forming discrete units. Space cannot compress indefinitely. When density reaches a critical threshold, quantum gravity produces a repulsive effect that prevents further compression. Instead of shrinking to a point, the universe undergoes a bounce. Before our expansion, there was a contracting phase. The singularity disappears, replaced by a transition from contraction to expansion. If this is correct, the universe did not begin in a single moment, it passed through a moment. Other models offer similar resolutions. In string theory, the universe might never reach zero size because strings cannot be compressed below a minimum length. Instead of collapsing to a singularity, the universe reaches a state of maximum density where standard physics no longer applies. In these states, new dimensions may unfold, or brains may collide and separate. The classical singularity becomes a phase transition, not an endpoint. Some cosmologists explore the possibility that the Big Bang was a quantum tunneling event, an emergence of space-time from a prior timeless state. In these models, there is no singular moment at all. Instead, the universe transitions from a quantum gravitational condition into classical expansion smoothly, without passing through a point of infinite density. The singularity, once again, fades away. Each of these scenarios shares a quiet theme. The singularity is not real. It is a boundary of knowledge, not a beginning of existence. But if the universe did not begin at a point, what is the shape of its beginning? Imagine a fog rather than a point. Imagine a region rather than a location. Imagine a process rather than an instant. In quantum cosmology, the earliest universe is described not by trajectories of particles, but by wave functions, probability distributions over possible geometries. These geometries overlap, fluctuate, and blend. The universe does not have a single history, but a superposition of histories. Time itself is not fundamental, but emerges as the universe settles into a classical configuration. In this image, the universe does not begin sharply. It condenses. Another way to picture the early universe is through Euclidean quantum gravity. In this approach, near the beginning, time behaves like a spatial dimension. Instead of a singular point, the universe resembles a smooth, rounded surface, finite, but without boundaries. Like the surface of a sphere, there is no edge, no sharp start. The universe simply transitions into existence without encountering a singular moment. Stephen Hawking famously described this idea by saying, "The universe has no boundary in time, just as the Earth has no edge in space. The singularity dissolves into geometry." But even this analogy is incomplete. The true nature of the earliest moment must be something stranger than our language allows, a boundary between classical spacetime and a deeper pre-spacetime reality. It is a region where time loses meaning, where light cannot propagate, where the distinction between before and after dissolves. In such a place, questions like, what happened before the Big Bang, may not have meaning in the traditional sense. The question assumes a timeline extending behind the earliest moment, but quantum gravity suggests that the timeline itself may dissolve near the boundary. There is no before, not because nothing existed, but because time had not yet emerged as a meaningful property. This is a subtle but profound difference. It shifts the question away from a moment that never existed and toward the conditions that allowed time to form. If there was no singular moment, then the universe's beginning was not a single explosion, but a transition from timelessness to time, from quantum fluctuation to geometric structure, from possibility to actuality. This realization reframes our understanding of cosmic origins. Instead of a beginning in the classical sense, the universe may have undergone a quantum birth, a smooth, probabilistic emergence from a deeper substrate. That substrate may have been another universe. It may have been an inflating field. It may have been a bouncing spacetime, or it may have been a timeless quantum gravitational state, but whatever it was not a singular point. As we close this chapter, one gentle thought remains. The singularity is not a door we pass through. It is a symbol on a map marking where our understanding ends. And beyond that boundary lies a landscape still hidden from us, waiting for the theories of tomorrow to illuminate its quiet, foundational truth. In the next chapter, we explore the deepest mystery of all, whether time itself existed before the universe, or whether time is a creation of the universe, arising only when space-time first settled into form. Part 14. The Arrow of Time. Why Time Flows Forward. Only after the Bang. Even if something existed before the Big Bang, time as we experience it, the flowing directional time, might not have existed. Here, we explore entropy, order, and the strange truth that time's arrow only appears when the universe has room to expand. To understand why time flows forward, imagine sitting quietly and watching a glass fall from a table. It shatters. The pieces scatter. The energy disperses. You know instantly which way time is moving, not because of clocks or calendars, but because order has given way to disorder. This transformation, the increasing spread of energy, the rise of entropy, is what tells you what future means. Without entropy increasing, time would feel directionless, suspended, almost frozen. Now, imagine the early universe. In its first moments, it was hot, dense, and incredibly uniform. Paradoxically, this uniformity represents low entropy. Even though the energy was immense, it was arranged in a way that allowed vast potential for disorder to grow. That growth of disorder, of structure forming and dissolving, is what gives the universe its arrow of time. But before the Big Bang, or before the universe entered its expanding phase, the situation may have been very different. Time, as we understand it, may not have flowed at all. To see why, we must drift gently into the heart of thermodynamics. Entropy is not simply disorder. It is the number of possible microscopic states consistent with what we see macroscopically. A gas spreading through a room has high entropy because countless microscopic arrangements are possible. A crystal has low entropy because its atoms are arranged in a precise pattern. In the early universe, matter and energy were not arranged in many possible ways. They were arranged in one peculiar, exquisitely fine-tuned way. Space was nearly uniform. Energy was distributed evenly. Gravity had not yet sculpted galaxies or stars. The universe was in a state that allowed entropy to increase dramatically as soon as expansion began. And as entropy increased, time found its direction. This raises a profound and quiet question. Why did the early universe begin in a low entropy state? Why did it start in a special configuration that allowed time to flow? Modern cosmology does not yet have a definitive answer, but several ideas offer glimpses into this mystery. One idea comes from inflation theory. Before the Big Bang's hot expansion, the universe may have been dominated by the inflaton field, a smooth, homogeneous field with minimal entropy. Inflation stretched this field, ironing out irregularities and producing the low entropy conditions needed for time to begin its forward march. In this picture, the arrow of time emerges naturally when inflation ends and entropy begins to rise. Another perspective arises from bouncing cosmologies. In a universe that contracts before expanding, the collapse phase might erase entropy. Gravitational structures flatten, horizons shrink, and chaotic arrangements become smooth. The bounce resets the universe's entropy to a low value, allowing the new arrow of time to point outward after expansion begins. In this view, each cycle has its own arrow of time, distinct from the one before. A third idea comes from quantum gravity. In quantum cosmology, time may not exist in the earliest states. The Wheeler-DeWitt equation, which attempts to combine quantum mechanics with gravity, has a remarkable property. It predicts a timeless universe at the deepest level. Only when the universe becomes large enough, structured enough, and classical enough does time emerge as a meaningful concept. In this framework, the arrow of time does not begin at the Big Bang, but arises when quantum uncertainty gives way to classical order. Time, then, is not fundamental. It is emergent. This idea can feel unsettling, but it follows naturally from what we know. In a perfectly symmetric, perfectly uniform universe, nothing changes, nothing flows, nothing evolves. Without change, the concept of before and after becomes meaningless. Time appears only when the universe contains enough structure to provide a sense of direction, and structure requires expansion. If the universe did not expand, entropy could not increase, gravity could not sculpt matter into galaxies, stars could not ignite, planets could not form, chemical reactions could not proceed with directionality. Life, which relies on the constant flow of energy from ordered states to disordered ones, would be impossible. The very fact that you experience time flowing forward is a direct consequence of the universe expanding into new possibilities. This leads us to a subtle but important realization. Time's arrow begins not at the Big Bang, but in the period immediately after it, when the universe becomes large enough to allow entropy to grow. Before that expansion, during the Planck era, or within a quantum gravitational state, time may have been undefined. The universe could have existed in a static, timeless condition. Only after the transition, Whether through inflation, a bounce, or a quantum tunneling event, could time acquire direction? Some physicists suggest that the arrow of time might reverse in a collapsing universe. As entropy decreases during contraction, if such a process is allowed, time might appear to flow backward relative to our experience. In such a universe, the future could look like increasing order. This is not merely a thought experiment. Certain cosmological models predict that at the apex of contraction, the arrow of time flips, producing a universe on the other side where time moves opposite to what we perceive. In that picture, the pre-Big Bang era, if it existed, may have had its own arrow of time, perhaps pointing in a direction we would consider backward. But backward is only a human interpretation. In each region of space-time, time flows in the direction of increasing entropy. What counts as forward is defined locally by the conditions within that universe. This leads to a profound and quiet symmetry. The universe on either side of the Big Bang may have had an arrow of time, but each arrow may point away from the Big Bang itself. In this view, the Big Bang is a point of lowest entropy, a moment from which time flows in two directions, forward for us, backward for another universe. The universe becomes not a single story, but a mirrored pair of stories joined at a central minimum of entropy. Time in each half moves outward, away from the point of highest order. This idea dissolves the need for a singular moment and instead replaces it with a symmetric system where the Big Bang sits at the center, not the beginning. Another perspective invites us to imagine the early universe as a boundary condition, an initial state imposed by the laws of physics. Certain theories propose that the universe's low entropy beginning is not accidental, but required. Perhaps the laws of nature demand a state of minimal entropy at the onset of classical spacetime. Perhaps the structure of quantum gravity leads naturally to such a state. Perhaps the uniformity of the early universe is not surprising but inevitable. As we contemplate these possibilities, one idea becomes clear. Time is not something that flows independently. It is sculpted by the universe's evolution. It arises from the configuration of matter and energy. It depends on expansion, structure, and entropy. And so, when we ask whether time existed before the Big Bang, we must be gentle with the question. We must recognize that our intuition, our sense of time as a constant river, breaks down near the origins of space-time. The river of time does not flow through those earliest regions. It begins only when the landscape allows it. As we leave this chapter, one quiet truth remains. The reason you feel time moving forward is because the universe is still unfolding, still expanding, still exploring the possibilities contained within its initial low entropy state. If the universe ever stops expanding, time may stop flowing. But for now, the arrow points onward, carried by the endless motion of entropy into the future. In the next chapter, we ask the final and most delicate question: whether any notion of before truly exists, or whether the universe's beginning is not a temporal boundary but a conceptual horizon. Part 15. Why the question still matters: the human pull toward origins. In the quiet hours of the night, this question returns: what came before? Even if physics cannot yet answer it, the search reveals something profound about our nature. We look backward because understanding our beginning gives shape to our place in the cosmos. In this final segment, we reflect on why the mystery itself brings comfort. To explore this gently, imagine yourself lying under a dark sky, listening to the faint hum of the universe that surrounds you. The stars are distant, their origins hidden behind billions of years. Yet you feel the pull of their story. You sense the presence of something older than any human memory, older than Earth, older than the galaxies themselves. And in that moment, a quiet curiosity rises. Where did all this come from? This question is not new. It echoes through ancient myths, philosophical musings, early scientific thought, and modern cosmology. Whether through stories of cosmic eggs, cycles of creation and destruction, divine sparks, or quantum fluctuations, humanity has always reached backward into darkness, searching for the first flicker of light. But why? Why does the question of origins matter so deeply to us? Part of the answer lies in our nature. Humans are pattern-seeking creatures. We trace causes to effects, stories to beginnings, rivers to sources. When we encounter something vast like the universe itself, the instinct to ask how it began is almost a form of gravity pulling at the mind. It feels incomplete not to know. It feels unsettling to imagine a cosmos without an explanation. Yet paradoxically, no matter how far science carries us, the question always recedes. If the universe began at the Big Bang, what came before the Big Bang? If cosmic inflation gave rise to our universe, what set the inflaton field in motion? If we live in a multiverse, what mechanism produces all the bubble universes? If quantum gravity removes the singularity, what preceded the bounce? Each answer opens a deeper layer, a new boundary, another horizon. And still, we keep asking. This persistent curiosity hints at something more than a desire for information. It hints at the human longing for context, for a frame that helps us understand our existence. When we ask what came before the universe, we are also asking where we belong within it. We are seeking a sense of continuity between ourselves and the cosmos. The search for origins is, in a quiet way, a search for belonging. It is also a search for meaning. Consider how profoundly origin stories shape human culture. Every civilization has one. Each story, whether mythic or scientific, offers a narrative about how order arose from chaos, how structure emerged from possibility, how life unfolded from the fabric of the cosmos. These stories do not just describe the universe, they give us a way to connect to it. Modern cosmology, though grounded in mathematics and observation, offers its own kind of narrative. It tells us that the atoms in our bodies were forged in stars, that time and space themselves evolved, that the universe had a childhood, a past, an arc of development. When we explore questions about the universe's beginning, we are exploring our own origins at the most fundamental level. But there is another, softer reason why the question matters. Asking what came before invites us into a space of wonder. It reminds us that the universe is larger than our understanding, deeper than our theories, older than our imagination. It humbles us gently, placing our lives within a scale so vast it becomes almost comforting. In a world full of uncertainty, the mystery of the cosmos offers a kind of stillness. The unknown becomes a refuge, a reminder that not everything must be solved to be meaningful. In recent years, as cosmologists have explored ideas like eternal inflation, cyclic universes, string-brain collisions, and quantum gravitational bounces, the scientific story has grown richer and more complex. But with every new model comes a new boundary. We discover mechanisms but not ultimate reasons. We uncover patterns but not final causes. The universe becomes more understandable and more mysterious at the same time. This duality is not a flaw of science, it is part of its beauty. Science illuminates the darkness without extinguishing the wonder that draws us toward the darkness in the first place. Even if we never fully answer the question of what came before the Big Bang, whether there was a before, whether time existed, whether another universe birthed ours, the search itself gives shape to our curiosity. It encourages us to think beyond our immediate lives, to reach into cosmic timescales, to consider the possibility that reality is far stranger and more beautiful than our senses suggest. There is comfort in knowing that some mysteries remain open. A closed universe of complete explanation might feel tidy, but it would leave little room for awe. A universe with unanswered questions invites us to keep imagining, keep learning, keep expanding the boundaries of human thought. And there is one more subtle comfort in the question. It connects us to every person who has ever looked up at the sky and wondered. Ancient astronomers watching the stars drift overhead, philosophers speculating about the first cause, medieval scholars tracing celestial motions, Enlightenment thinkers debating cosmic origins, modern physicists probing the Planck scale, ordinary people lying under quiet skies, feeling small and infinite at the same time. The question of origins binds us across cultures, across eras, across ways of knowing. It is a thread woven through human history. In this sense, the question, what came before the Big Bang, is not only about cosmology, It is about humanity. It is about the feeling of being part of something immense, something continuous, something profoundly mysterious. It is about the desire to understand where we come from, not just biologically or culturally, but cosmically. And even if physics one day answers the question, the human impulse to wonder will remain. For every boundary we cross reveals a deeper boundary waiting beyond it. The universe, it seems, is structured not only in layers of matter and energy, but in layers of meaning. As we drift gently toward the end of this final chapter, one feeling rises quietly. The mystery itself is not a gap in knowledge. It is a form of connection. It reminds us that we are part of a story still unfolding, still expanding, still full of questions that guide us toward deeper understanding. And so, the question matters, not because of the answer, but because of the journey it opens. A journey into the origins of the cosmos, a journey into the limits of time and space, a journey into ourselves. In this quiet reflection, we find comfort. The universe may not give us a final answer yet, but it gives us something just as profound, the invitation to keep wondering.